Hi, I'm Leah Evans, and I'm an engineer here at ON Semiconductor. Today, we would like to discuss our power MOSFET solutions, and especially the advanced thin Atpak package, which has excellent thermal performance. It is intended for use in switching device applications. Currently, there is a great demand for low power consumption and energy-saving electronic products to meet and exceed the energy savings requirements from governmental and industry standards organizations. The power MOSFET has become the standard choice as the main switching device due to low switching losses. Thinner and smaller electronic devices are becoming more prevalent in consumer electronics. The power supply accounts for a large part of the electronic component blocks in terms of both space and weight. Because it is required for design engineers to improve the overall power supply efficiency, a reduction in power loss while allowing large load currents has become more important. Of course, the required mounting space and the weight always need to be reduced. Power MOSFETs offer excellent performance in high-speed switching, high breakdown voltage, high current, and low power loss. They are excellent in high-speed, high-frequency operation. Power MOSFETs are widely used in switching regulators such as AC-DC or DC-DC converters and motor controllers. Power MOSFETs consist of 3 electrodes: gate, source, and drain. Using a trench structure inside the silicon as the gate, the current path builds up between source upper and drain lower. If an N-channel is located directly under the oxide film of the gate or N-channel MOSFET, electrons are collected there, and in the opposite case, or P-channel MOSFET, electron holes are generated in the P-channel directly underneath the oxide film. The current flows vertically between drain and source. The trench structure makes integration easier and results in a lower on resistance, or RDS. Breakdown voltage between drain and source, or BVDSS, and on resistance, or RDS, are the significant parameters. The breakdown voltage between drain and source refers to the maximum voltage, or VDSS, you can apply between drain and source. You need to select the right breakdown voltage between drain and source according to the supply voltage and the required design margin. On resistance refers to the resistance to the current flowing from drain to source. On resistance and breakdown voltage between drain and source are in a trade-off relationship. In general, the higher the breakdown voltage, the higher the on resistance becomes for devices with the same die size. When you select a power MOSFET, make sure that you select a device with both drain source breakdown voltage and on resistance matching your application requirements. But before you select a power MOSFET for switching applications, you would need to understand the following additional characteristics. There are several challenges you need to consider: switching speed, temperature, voltage, avalanche capacity, and package. Switching speed correlates to the total gate charge that needs to be charged or discharged in the gate drive circuit, QG. It is critical to choose whether you need to minimize the on resistance or to accommodate fast switching speed by keeping the gate charge under control when designing a MOSFET. For the development engineer of the application, it is important to choose the optimum MOSFET and trade off on resistance power loss versus switching power loss for the given application. The other challenge is to minimize temperature. In other words, engineers need to select a device that does not exceed a designated temperature when they design applications. Meanwhile, you need to make applications smaller and thinner to meet market demands. As package size gets smaller, the temperature inside of the device tends to get higher as it becomes more difficult to extract excess heat. This is a challenge for engineers to accomplish 2 contradictory design requirements. Power density refers to power per unit area or unit volume or unit weight. The allowable power loss of a power MOSFET is limited depending on a particular application. In a design, the power consumption needs to be below the allowable power loss. Avalanche capacity refers to the level of susceptibility when energy stored in an inductance is discharged into a power MOSFET. During the design, avalanche energy and avalanche current have to be taken into consideration. As for the package, there are 2 package types: A surface mounting package is used for mobile phones and small components such as smartphones and PCs. A through-hole package is used for a power supply and for industrial equipment. Each application has its own thermal resistance, and you need to select package and device according to your application requirements. ON Semiconductor's cutting-edge Atpak Power MOSFET package was designed to overcome those challenges mentioned earlier. One of the features of the Atpak package is low height. Compared to the industry standard D-Pak package size, the Atpak reduces the height by 35% while maintaining the same footprint. From the cost standpoint, the cost of the Atpak is nearly the same as the D-Pak, but smaller and more efficient, making it a good replacement for your design consideration. We have also adopted clip bonding technology in order to minimize thermal resistance, RTH, to minimize on resistance, RDS on, and to increase current capability, ID max. Formerly, we used wire bonding technology using gold, copper, or aluminum wires in order to connect each electrode on the silicon chip in the package. However, since each wire is relatively thin, it is difficult to allow higher load currents without excess losses. We successfully reduced the on resistance and realized better thermal conduction by connecting each electrode directly with the copper clip, overcoming those disadvantages. The structure of clip bonding technology uses a copper plate with a wide section area. This enables the increase of total full load current without concern for the fusing current that occurs in conventional wire bonding. In applications where the on resistance is required to be lower than 10 milliohms, the resistance in the wire, approximately a couple of milliohms, cannot be ignored. In the Atpak package with clip bonding technology, by deploying a copper clip with a wider cross-section area compared to gold, copper, and aluminum wires, results in a drastic reduction in the electrical resistance in the source drain paths to the external pins. The resulting reduction is on the order of 90% compared to gold wire, and by 30% compared to aluminum wire. Besides the advantage of the Atpak in size, as I mentioned earlier, the package cost is about the same as the D-Pak package cost. Therefore, the Atpak can be a replacement for the current D-Pak package power MOSFETs with better characteristics. We conducted a benchmark test between our Atpak and the D-Pak using the evaluation board shown. We measured the temperatures using thermograph equipment. We ignored the impact of the board on the heatsink since we mounted the Atpak and the D-Pak on the same position on the evaluation board. The MOSFETs were both controlled to dissipate 1.44 watts and the temperatures were recorded. Here you can see the temperature comparison of the Atpak versus the D-Pak. Here are the results over time. You see that the surface temperature of the D-Pak package reached 80 degrees, whereas the surface temperature of the Atpak package reached only 74.8 degrees. This is a temperature difference of 5.2 degrees. If we estimate the junction temperature based on the thermal resistance, our calculation shows that the gap was approximately 6.2 degrees, which validated the test result. The table here summarizes the test result. Power MOSFETs in the Atpak package are used for a variety of end applications. Among these, there are DC-DC converters using low voltage and medium voltage MOSFETs, primary stage power supplies using high voltage MOSFETs, and secondary stage power supplies, various motor drivers, and multi-cell lithium-ion battery protection circuits using low voltage and medium voltage MOSFETs. ON Semiconductor offers a wide range of parts for P-channel applications. We have the most diverse product portfolio in the market today. We also offer a wide range of N-channel power MOSFETs. Our portfolio allows you to select the MOSFETs based on the breakdown voltage or based on resistance and gate voltage in order to find the optimum device matching your application needs. For more detail regarding the complete portfolio of ON Semiconductor Atpak MOSFETs, please contact your local ON Semiconductor sales representative or authorized distributor. For more information about the ON Semiconductor Atpak Power MOSFET products, visit us on the web at www.onsemi.com. Thank you.